Our next speaker, I will turn my little guide off. We're following in the range is Andrew Broomfield. He's from Elizabeth City State, if I am not mistaken.
All right, there we go. Okay, good afternoon, everyone. My name is Andrew Brumfield. I am from Holly Springs, North Carolina, so I've been a native of this area for a long time. And I am a graduate of Elizabeth City State University with an engineering, technology, mechanical, and automation undergraduate degree, and recently received my master's degree in mathematics with a concentration in remote sensing. Today, I'm here to present my master's thesis work that I've done this past spring. I completed this past spring. I've also had the opportunity to present a poster presentation at Science Gateway's conference at San Diego Supercomputing Lab. So that was a great opportunity, and I also presented during Research Week at Elizabeth City State University. So I hope to give you guys the wonderful presentation that I was able to give them. So first, I'm just going to briefly go a little bit over my abstract. I'm not going to go over the whole thing for the sake of time. But the Sargassum Sea has been a marine life habitat for millions of years, located in the North Atlantic subtropical gyre, with the western limit formed by the north and northeastern flowing powerful Gulf Stream. The importance of the Sargassum Sea is recognized for the role of its current system providing shelter and protection for marine life such as fish and sea turtles. Two species of sargassum, S. natans and S. flutans, are highly branched with thalassus with numerous pneumocysts that contain oxygen, nitrogen, and carbon dioxide to give buoyancy to the brown algae. Sea surface winds can cause sargassum to aggregate and form lengthy windrow rafts to propagate. And as these pneumocysts lose their buoyancy and lose their gases, sargassum can reach up to 100 meters below the sea surface, or even accumulate on the sea floor. Accurate mapping of the boundary in the local area of the Gulf Stream near the coast of Cape Hatteras, extending to the Bermuda area, has yet to be conducted using Earth-absorbing Landsat satellites. And that's mostly what I'm going to cover on my abstract. But the reason we want to cover most of the Sargassum Sea is because it is an indicator of acidification of the ocean, in which when acidification goes on, we start losing marine life. Once we start losing marine life, we start losing our ability to catch fish and use them for food. So if we lose our food, who knows what's going to happen? So we need to make sure that the ocean is still going. A lot of marine life use this large area. As you can see, it's almost the size of North America, just the amount of states that we preside in, that marine life go and use as a protection area and a habitat, and also a feeding ground for some predators of the sea to eat. So if this disappears, what's going to happen? We also have other problems with sargassum, is that it tends to propagate and end up on travel areas, such as beaches. And once it's there, it's really horrible to smell, really bad to look at on a vacation that you just spent thousands of dollars to come out to. So a lot of this detection system can be used to protect from sargassum showing up on the sea. And I can see Google Docs kind of messed me up here. Let's see next. So we've had things that have affected the Sargassum Sea, such as sea level rising and the Deep Horizon oil spill. But that's mostly because most of the sargassum is generated from the Gulf of Mexico, and through the Gulf, it travels up the Gulf, if I show you here, travels up this Gulf Stream and protrudes past the coast of North Carolina into the Sargassum Sea. So whatever's going on here is very important to know what's going to happen to the rest of the Sargassum Sea, even though it was capped 87 days later, but we're not really too worried about that anymore. So for my considerations, I wanted to start mapping near the coast where sargassum from the Gulf of Mexico ends up into the Sargassum Sea. So I want to use Landsat satellites since they mostly are covering the coastal areas and near the coast. And also its resolution is 30 by 30 meter resolution, which can also be interpolated to 15 by 15 meter resolution if needed. The resolution that I received most of my through my publications of reading how to detect sargassum in the sea, they were using MODIS data from Terra and Aqua, which their resolution is 500 meters of resolution. And like I said in my abstract, sargassum can form lengthy, very thin rim rows in the ocean due to the wind. So the indexes that I wanted to use to identify sargassum, which is depicted here, was the floating algae index, which was utilized in a research done in the Yellow Sea, which they took the algorithm and utilized it with MODIS data and made a monthly composite of the values that had an uptick in the floating algae index. That was wonderful, but obviously the Sargassum Sea is in the ocean and it's a lot more dynamic than the Yellow Sea. First, so here's the algorithm here, which I also use NDVI, which is a vegetation index, normalized vegetation index, to correlate with that data to know what I'm looking at when I process the data. Also, the one problem that I had to solve was identifying which bands on the Landsat 7 and Landsat 8 detection sensors according to the MODIS data that was used. So most of my data was collected from the United States Geological Survey. They provide a database of all satellites, public information that I can download straight to my computer. Good thing about Elizabeth City State University is that we are also a direct broadcast station, so we can download, we receive information straight from the satellites instead of through USGS. But for Landsat, we don't have the licenses for it, so this is the way I use it. So image selection was important, and the timeline was important, which was May through August, and the location was mostly over the coast of Cape Hatteras, right here. So a good thing is USGS has everything blocked off into nice little chunks, and I can just say, hey, I just want from these block areas according to the parameters that I need. So NV was what I used to process these geotiffs that were provided from USGS, and they were used in identifying sargassum that's in these images and in the sea. Well, I don't know if this wonderful video is going to play. Okay, no, it's not. I think it is. Ooh, don't know what happened there. Excuse me one second. Oh. I think this will work. Okay, we won't do that then. Okay, but this had a video of how the information was processed. What had to happen was through my first time using the floating algae index, I didn't get very positive values. I didn't even really get an index. It was very, very small numbers, and I was wondering what was going on there. Well, what happened was that I had to convert the reflectance values into radiance values first, and then use the band math operation in NV to create my floating algae indexes, and as well as normalized vegetation indexes. So here's the results, and most of my videos showed how those two images were linked together. But this is off near the Bermuda area, and that's pause. Off at the Bermuda area, and this is a RGB, which is a red, blue, and green image, and then here's a floating, the NDVI here. So what I did for the Cape Hatteras areas, what I did a RGB so I can tell what is the ground, what is water, and what might be clouds. Because cloud cover was mostly my main enemy in this research. Here's NDVI. As you can tell, the vegetation index is very high in the grass areas, and obviously not so much in this area, but you see NDVI values of some sort of positive in the ocean areas. And then here's a floating algae index, which is a real mess. But yet here, what I'm seeing, which was shown in the video, was that we had very high and very positive floating algae indexes in shallow water. And the reason why I wanted to use that along with NDVI is because I didn't want to say, okay, this right here is sargassum because of the positive values. And then when I go back to NDVI, I still see the same thing, but yet this could be clouds. And this could be cloud cover because of the high radiance values there. So for future work, because of cloud cover being such an obstruction constantly throughout the years in the data flow, we think, well, what can we do to eliminate cloud cover? Well, we should probably go underneath the clouds. And so a combination of establishing a new monitoring system would be the goal of my future work, which would be using a buoy and drone system in combination to send the data and also to be a powering station for those drones in those areas to complement satellite imagery as well. Because these things can go from one spot, fly really high, and gather the information and then send it through the buoy system and complement satellite information, where cloud cover could be covering at all times, since the ocean is a cloud factory for some reason. So that's what I want to do for the future work, because I didn't want to say, hey, with my results, we can't have any idea of what's going on with the boundary area. So this will help identify the boundary area in a better way. And as I was talking with my mentor last night, I was going to be presenting this work, I suggested, well, we do have an International Space Station so that we can do experiments in space without having to travel there and then travel back. Well, how come there isn't any type of research center out in the Sargassum Sea when we see how huge it is and how diverse, and there's marine life that needs to be studied as well? So I'm thinking the same method should be used as well, also to maintain the system as well. We don't want the buoy system in all of the Sargassum Sea, but mostly in the boundary to see if it's shrinking or growing, because we need to know that due to the change in the climate. Here's a few of my references, just in case. And are there any questions? Before I get to questions, I would like to acknowledge Dr. Hayden as my principal investigator throughout my years in SERSR, and my mentor, Dr. Robert George, who got me interested into this wonderful study.
You were using Landsat 7. Was that all striking? Were there no good images on A? Or was that just artifacted?
For 8 was new, and not many images were of the far waters area, mostly just in the mainland of the United States. Landsat 7 for some reason had more coastal area imagery, so I was able to get out at least 2 rows and 2 columns out into the ocean because of the way North Carolina is curved that way for you guys. North Carolina's curved. There's a lot of open area over here. So that's the reason why Landsat 7 mostly showed up in most of the images.
So you did a great radiance. You did a documented subtraction values of the radiance.
Yes, that was a main issue because I already processed many images, and a lot of cloud cover was in the way, but the index was between -0 and 2, but only small values. And that's how I realized, okay, I'm doing something wrong. And I went through the publications again and found out that correction for radiance need to happen. Yes, sir. Yeah, that's a great question, because for drones and putting a multispectral imager on there would be a lot better as well. Obviously, the satellites, they have multispectral sensors as well, but not on Landsat or any public ones. But just in the same sense we use for field work, we use multispectral imagery to classify items. We want to use the same method as well. So we want to add more channels, add more spectrals, and to identify what exactly is not water and what it is sargassum and part of the Sargassum Sea. Or even if some marine life pops up, we would like to know what that is as well, instead of just an anomaly. So absolutely. Yes. No, I just mostly focused on Landsat imagery and the spectrals that are available on that one, because of the resolution, 50 by 50 meter resolution, because of the feature that I'm looking for can be very lengthy and not so much spread out. So 500 meter resolution probably would have had more spectrals, but it wouldn't be optimal for identifying what I'm looking for. Yeah, and that's a good reason why I want to use drones as well, because we can go straight from the surface to do great classification without having to always be there. And then we can go high in altitude and cover a large area and still have great resolution and great accuracy as well. That's why fixed wings would be kind of out of the picture, because we have to fly it out and hopefully come back and then repeat. And with this method, with multiple sensors in different areas of the Sargassum Sea, they can all go up at once and all go down at once, and we won't have separation in times of information, because same thing with satellites, they don't always go over the same exact spot at the same exact time at different days. This way we can control most of that time.
All right. Thank you very much.
Thank you.